Okay, so we're going to go ahead and start. Hello, everyone. Welcome to today's SciML webinar. Today, we're excited to have Bowen Deng giving the talk and Professor Ridwan Sakidja as our session chair. Professor Sakidja is a professor at Physics and Material Science for the Physics and Material Science faculty at Missouri State University. His group works on computational material science in general and on the interatomic potential development. He graduated from the University of Wisconsin-Madison and worked under Professors Dane Morgan and John Perez-Pezco. He's also worked with Professor Kirsten Person's group at the Materials Project group at Berkeley. With that, thank you for joining us, Professor Sakidja. I'll hand it over to you.
Thank you very much, Keith. This is an extremely, I think, great opportunity. I want to be able to thank, obviously, the organizer for having such a wonderful event like this. So let's get to the main event. I want to introduce Bowen Deng. He is a student, PhD candidate at the Department of Material Science and Engineering Department at UC Berkeley. He works under the supervision of Professor Gerd Cedar, and he's been working with essentially that intersection of material science and artificial intelligence. So one of these main sort of area of focus in terms of research is looking at one of those forefront in terms of the challenges with respect to energy storage. And in turn also about discovering new materials. And with that, he combined deep learning, first principle or ab-initio simulations, thermodynamics, and of course statistical mechanics. So I'm very excited about this, and I thank the organizer for having this to be 2 hours. If I can say the only limitation I see is that I wish this becomes 3 hours, like a Lex Friedman podcast, for example. So without further ado, Bowen, take it away.
Yeah, thank you so much. Thank you so much, Professor Sakidja, for the nice introduction. And thanks, Case, again, for arranging for this really nice SciML webinar series. So hi, everyone. Let's get started. My name is Bowen Deng, and today I'm going to share about some of our recent progresses development of this pre-trained universal interatomic potential for charge-informed atomistic modeling. And the model we give the name CHGNet. So today's agenda is mostly consists of 5 steps. The first of all, I'm going to give a brief introduction on atomic simulations and the machine learning interatomic potentials. And the second of all, I'm going to give an introduction on the motivation and formalism of our model CHGNet. And thirdly, I'm going to give some benchmark results on the performances and reliability of CHGNet model. And next, I'm going to show you some applications that we apply this CHGNet interatomic potential to really study the problems that we have in energy storage materials. And at last, I'm going to show you some code examples that hopefully can help you apply these universal interatomic potentials in your research areas. So what is atomistic simulations? So we all know atomistic simulations like molecular dynamics provides us a lot of ways to design new materials and understand their underlying mechanism. And for example, this has been applied to drug discovery, energy storage, catalysis, mechanical and functional materials, etc. And here what I'm going to show you is a video of the simulation of the melting of ice into water. And this is done through a classical molecular dynamics, through a classical force field. So you can see the gradual movement and the larger perturbation of these H2O molecules, and finally they melted. So how are it possible to simulate like these realistic materials and chemical systems? And what lies at the heart of all of these simulations are these interatomic potentials, which provides the driven forces for all of these modelings. For example, at the heart of this molecular dynamics is an interatomic potential, also known as force field, that actually provides the force and energy of a given set of atoms. If you have a given set of atoms, and the interatomic potentials can essentially predict the movement of the systems, and we can iteratively update the lattice and atom locations to simulate a dynamic process. So there do exist different kinds of interatomic potentials for people to use, and they range from from the end of a high accuracy to the end of high efficiency, and obviously there's a trade-off between them. At the most accurate side, we have this ab-initio molecular dynamics, which essentially people solve the self-consistent electron density field to obtain the energy and force for given sets of atoms under the formulation of density functional theory. But unfortunately, the cost of these AIMDs usually scales cubically with the number of atoms, which essentially prevents their application for large-scale simulations. On the other hand, we have these classical force fields, which are essentially empirical functional forms that are fitted with few parameters like electrostatics and Lennard-Jones potential, where you have a linear cost with the number of atoms, but often they are considered not accurate enough to model all the complicated phenomena that happen at atomic scale. And in recent years, there has been growing effort in building these machine learning interatomic potentials, which in short we call MLIP, which are data-centric, and that tries to bridge the effectiveness and the accuracies from both sides. So here we have a weak assumption on the functional forms that we use, and we fit the many parameters of machine learning interatomic potentials to a very large data set that is usually generated by those high accuracy simulation tools like the AIMDs. And the cost of these MLIPs are also linear with the number of atoms as shown on the right plot. So what lies behind these machine learning interatomic potentials? The idea is actually not that hard. The key idea is that we have a black box function that maps the local descriptors from atom environments within a cutoff radius to the energy of the center atom, while forcing the proper symmetry constraints. And the weights of these black box functions are trained to minimize the error compared to first principle energy and force labels. There have been a very fast development over the past 15 years in the MLIP field. And starting from year 2007, we have the BP potential, which is considered as the first NM potential. And then we really see the smart people around the world start to build better descriptors and more physical constraints into the formulation of these machine learning potentials, like GAP and graph models. And also now you have all these equivariant models like CHGNet and equip. And on the other hand, we also see the striking of the power of modern AI that drives the field into increased data and model size. And you start to see this more universal model and this giant models trained on massive data sets. And as the reliability and the accuracy of these MLIPs gets developed and better assessed, we see increasing MLIP applications in materials and chemistry modeling. And today I'm going to talk about two limitations and our contributions with CHGNet work that addresses these issues. And the first limitations we want to bring up is the expressibility issue that we realized most machine learning atomic potentials describe only atomic systems with the nucleus charge. Basically, they only treat the systems as a cloud of nucleus positions with only the nucleus charge as their identity. So can we actually use this machine learning interatomic potential to describe the distribution of the electrons and the valence states? And the second problem that we want to talk about is where most machine learning interatomic potentials are trained and applied to a specific system or narrow chemistry, can we reuse our model and data from one system to another? And can we pre-train a foundation model that really serves as a baseline for all the downstream tasks to make all the downstream tasks more efficiency and more accurate? So speaking about charge, charge is really a very important aspect in atomistic modeling, and it's a central component in describing chemical reactions, phase transformations, and entropy effects. The importance of ions' valence states comes from the fact that the ion can engage in very different bonding with its environment depending on its valence states. For example, here, in ionic systems, the high-valent manganese 4+ ions are often considered as immobile spherical ion that only ever resides in the octahedral coordination by oxygen atoms. Manganese 3+ is a Young-Taylor active ion that tends to radically distort its local environment, leading to an anisotropically distorted octahedral framework. Manganese 2+ is a highly mobile ion that tends to sit in this tetrahedral coordination with oxygen ions. And we often consider them as highly mobile, so they really want to diffuse within the system. And however, without the explicit representation of these atomic charges, it is really impossible for us to study these complicated charge interactions like the manganese case. So let's take a look at how charge has been represented in quantum mechanics. So in density functional theory, a full description of charge can be seen on the left plot, where we have the charge density distribution within the atomic systems. However, such full description of charge is often considered too complicated to scale to a large scale simulations. We really don't want to represent the charge density at every point in the space when we scale to a very large scale and long time simulation, and these are really inefficient. So let's take a look at if there's another way to represent this charge. So luckily, we have been found that in spin polarized DFT calculations, the atom-wise magnetic moment, in short magmom, derives from the difference in localized upspin and downspin electron densities is actually a very good representation of coarse-grained atomic charge. For example, on the right plot, the three different peaks of magmoms ranging from 3.0 to 4.6 correspond to the distribution of manganese 4+, 3+, and 2+. Multiple previous researches have demonstrated the usage of magmoms to enable the study of electron interactions like charge transfer and electronic entropy. So the question to us is, can we really build this coarse-grained charge information, also here we mean magmoms, into the formulation of machine learning interatomic potentials, and can we use these electrons representations to enhance its description and physicality? To answer this question, let's take a look at how atoms are actually represented in machine learning interatomic potentials. So in our work, we use a crystal graph as a representation for periodic materials, and these crystal graphs are constructed by searching for the neighboring atoms for each atom within a cutoff radius. For example, if you look at the lithium manganese oxide unit cell on the left here, using a 2.8 angstrom cutoff radius, you get this atom graph on the right. And the color corresponds to each types of atoms. So you can see, for example, the manganese should have 6 neighbors here. So it has 6 bonds connecting to different nodes. And by constructing these crystal graphs, we only keep the relative interatomic coordinates between the atoms. So these crystal graphs benefits from translational, rotational, permutational, parity, and supercell invariance. Mathematically, the crystal graph is represented by an adjacency list where you specify the starting and ending node of each paired nodes, and also we have the information of the edges between them that specify here the pairwise distance. And likewise, in addition to the atom graph, we also have a bond graph that considers the angle as the pairwise information between bonds. So as the same way that we construct atom graph, where each node is an atom feature and each bond is a bond feature between the paired atoms, we can also construct this bond graph, where each node is a bond feature and each edge connecting two nodes are actually angle features. So in this way, we explicitly include the three-body interactions within the formulation of our machine learning interatomic potentials. And after we have constructed this atom graph and bond graphs, we pass them into these deep learning models, where at the first step, we actually tries to basis expand this bond and angle informations, and in a machine learning language, we embed them into high-dimensional hidden vectors. So the bond distances are expanded by the smooth radial Bessel functions, and the angle informations are expanded by Fourier expansions. And after these embedding layers, where I show in the yellow color blocks here, these high-dimensional vectors are updated through these interaction blocks, where we simulate the information transfer between the atoms. And this interaction blocks contains essentially 3 layers, where we iteratively update the atom, bond, and angle features that are predefined by the relationship, the pairwise relationship in the atom graph and the bond graph. So if you look at what happens within each convolution layer, it's really a simple process. So we basically tries to search for all the neighboring atoms for each atom, and in this case, it's for the atom graph. So we search for all the neighbors for each nodes, and we compute their pairwise messages, and then we aggregate them to the receiver node. And that's how an atom can receive the message and information from all of its neighboring cells and neighboring atoms. And after we simulate, we perform n interaction blocks, which in our pretrained model, we use 4 interaction blocks. We reach the effectively 20 angstrom interaction radius, and also many body interactions. And after all of these interaction blocks, we predict the properties of the crystal structures by these readout layers. So first of all, we use a linear layer to map the features on the atoms to the corresponding magnetic moments of the atom. And in such a way, we apply these charge constraints to this atom embeddings to force that they must have the information of their atomic charge. And second of all, we predict the total energy of the system using this non-linear mapping of the atom embeddings and the summation over them. And the forces and the stresses can be calculated through auto differentiation of the total energy with respect to the atom coordinates and the cell. And to train this giant neural network, we use a combined loss function that contains terms from the energy, the force, the stress, and the magmums. So for a summary, the workflow of our model called Crystal Hamiltonian Graph Neural Network, in short CHGNet, is listed as follows. A crystal with an unknown charge state is used as input, and we send it to CHGNet, where we use both 2-body message passing layers and 3-body interaction layers to calculate the energy, force, stress, and magmums of the given crystal. And different from previous machine learning interatomic potentials, we regularize the node-wise features, which represent the atom information, to the magmums associated with the corresponding sites, such that the atom features are forced to contain information about atomic charge. As a result, mixed valence state ions like manganese 3 and manganese 4 will have a different interaction as represented in the graph neural network, even if they were provided with the same elemental labels. So as a result, we can represent this distinguished behavior of different type of valences within the formulation of CHGNet. I see there's a question raised by Kate.
Yeah, I have a quick question about how you, I guess, conserve the charge at the end. Is it like a classification kind of system? How do you make sure the charge totals to 0 and for the full graph?
Yeah, that's a great question. So first of all, the charge here are represented by magnetic moments. So we don't really use the some of the models, for example, use charge equilibration methods to just predict the charge of each atom and then try to equilibrate them through some scheme. In our work, we were targeted as the trying to directly predict the charge that comes from the DFT functional theories, density functional theories. One of the reasons is that we believe a lot of the complicated interactions of these different valence states of of these heterovalent ions cannot be captured by classical charge equilibration methods. And that's why we use these density functional theory labels, and we try to predict them directly from these node features. And since these node features also are used to calculate the energy, so the energy calculation is actually conditioned on the charge prediction. Does that answer your question?
So you don't actually predict these 2 plus 2 minus charges. You predict the magmoms.
Yeah, but the magmom to charge have a 1-to-1 mapping.
Okay.
Yeah.
Okay.
Yeah, if I may chime in here. I forgot to mention that actually your paper actually is featured in the cover of Nature Machine Intelligence. Bowen is very, very humble, and it's not telling you at the get-go. So I'm gonna just chime in there on that. And then the other thing also, I just mentioned that it is also already described in the paper as well about the global is not included in terms of for charge that, as you alluded to. However, the error for your magnetic moment is extremely low.
Yes, true. True. So as what Professor Sakidja has been said, the global charge neutrality is not strictly enforced under the formulation of charge inference by magnetic moments. This has been a challenging task since you will need to have some spontaneous symmetry breaking within these graph neural networks to enforce the strict global charge neutrality. But in application, we have seen that the prediction of CHGNet for most of the time satisfy global charge neutrality, so which is a good sign. Yeah, so I'll continue the next slide. So to train this our model called CHGNet, we really looked into the resource of the this current available data sets where we can get the most amount of reliable data, and that's why we come to the materials project. And materials project has been arised in recent years as one of the mostly widely popular and widely used database for these inorganic materials and also some molecules. And also in recent years has been becoming a baseline for all of these machine learning applications and the benchmarks. So to train CHGNet, we went into materials project, and the materials project has done more than 1 million calculation tasks over the past 10 years with density functional theory. And we collected all of these calculations, and we parsed them into a giant data set and make sure the compatibility of the data points within our data set. And we also want to avoid duplicated training data points. And this data set really spans from almost all chemistries within the inorganic crystalline materials. And here is a list of complicated parsing criterion that we used last year to parse this data set. Basically, we ensure their computation consistency, like we don't want different functionals to have inconsistent calculations like a plus U value inconsistency, and we like K points. And we also make sure their structure uniqueness by checking whether the structures are too similar to each other. And we also figure out the outliers by checking, for example, electronic steps and whether the frames has very weird labels. So by this effort, we reached the 1.5 million structures from this 146K compounds from materials project, and we achieved more than 100K occurrences for 60 elements with more than 10K magmoms or for 76 elements. And here is a distribution on the elements within the MP trajectory dataset. So you can see we have a considerable coverage of almost all chemistry excluding only the noble gases and actinoids. And by this effort, we really more than 10 times expanded the previous largest training data set, which I believe comes from, speaking about inorganic materials, comes from the M3GNet paper, and which ends up in this more than 1 million atoms, more than 1 million structures data set, which we call MP trajectory data set. And we have trained our CHGNet model on this giant MP trajectory data set. So here are the test set mean absolute errors. On the top part is the CHGNet 0.20, which we use the 8:1:1 splittings. At the end, we achieved 30 MeV per atom, 77 MeV per angstrom, and 0.348 GPar for stress, and 0.032 μb for magma. And this is the version that we published with the paper, and we just released actually another version, which we call CHGNet version 0.30, which we trained with a 9 to 0.5 to 0.5 splittings, and we achieved a slightly better result, especially on the test set and validation set. But most people know that it's actually not that convincing. If you really want to assess the model's performance, you do not really want to look only at the test set performance. So that's why we come to this benchmark test to see really the performance of our models. And in this benchmark, we goes into this MathBench discovery, which is a new materials discovery benchmark that essentially we apply these machine learning models that tries to discover stable materials from a pool of 256K hypothetical structures that were calculated from single element substitution with materials project data and the density functional theory. And this data set itself, which I believe is called the WBM data set, has a very wide span of chemical systems that and actually even have more structures than materials project itself. So the task we have now is, can we really use these machine learning models to identify the stable phases out of these giant pools that were identified with DFT? So we apply CHGNet to this MathBench discovery task, and surprisingly, actually, CHGNet achieves the best result within this pool of models that we have applied for this test. And these models include a lot of the well-known models like M3GNet and CHGNet, and also you can see there are equivariant models, MACE, which have a slightly lower accuracy than CHGNet. And besides this benchmark tests on new materials discovery, we're also interested to see whether we can apply these pre-trained foundation models like CHGNet to simulate dynamic process reliably. But these dynamic process benchmarks are noticeably much harder than the benchmark for new material discovery, since the ground truth of these dynamic properties is not easily accessible. And you should know that to simulate just a single diffusivity of one of these materials, it typically requires several weeks and up to months. So we use the available AIMD results from a recent lithium solid-state superionic conductor paper, where the previous researchers studied the ionic diffusivities on these 10 types of different lithium superionic conductors. So we applied the pre-trained CHGNet to simulate the molecular dynamics at elevated temperature, and just in the exactly same process as what is mentioned in this previous paper, and we extrapolated them to room temperature and observed the room temperature conductivities and also the activation energies. And what we have observed there is CHGNet has a perfect agreement with the AIMD simulated diffusivities with all of the actually all of these data points within the AIMD error bars, and with only zero-shot inference. So CHGNet has learned nothing on these trajectories, but is able to predict which conductors are better than the others as discovered by DFT. And the next slides, I want to give a discussion on one of the, I guess is now widely discussed topic, that whether we can use this pre-trained machine learning interactive potentials and fine-tune on your own system of interest to achieve a better result than training a model from scratch. And here I show some of our result of fine-tuning CHGNet in this lithium zirconium chloride system, where here we use the lithium zirconium chloride AMD trajectories to either fine-tune or train a CHGNet from scratch and observe the performance difference. And we compare the performance of relaxation and energy evaluations on an ensemble of lithium zirconium chloride cells with different cation orderings. And here what we have found is that in the interpolation domain, where only lithium vacancy disorder is considered, there is really negligible difference of your training strategy. So you can see these three curves almost agree with each other. So we really don't care if we have enough data within this interpolation domain. However, when the model is extrapolated to these fully disordered structures where we randomly distributed the zirconium sites, and the zirconium sites orderings are actually extremely rare events to be sampled within this fine-tuned data set. As you can see, these are these star points in DFT tells you that they have very high energies compared to all of these green parts. So that's an indication that you really cannot sample these events in the AMD. And in this region, the pre-training plus fine-tuning strategy achieves a much better and much robust result than just training CHGNet from scratch. And this result highlights the importance of generalization effect from a comprehensive pre-trained dataset and shows the advantage of foundation models like CHGNet can enable a faster and more reliable fine-tuning downstream task. So after talking about these benchmarks we have done with CHGNet here, I want to show you a few applications that we really apply CHGNet to solve in energy storage materials. And the first example I want to show you is how we do charge inference in these MVP Nasican structures. So we've randomly removed half of the sodium ions from MVP supercell with more than 2,000 atoms that is shown on the left, and we relax the structures with CHGNet. So the pristine, unrelaxed, and relaxed structures are labeled in these black, blue, and orange fonts. And if you calculate the oxidation state simply from the change of composition, since we know that the sodium ions, the P and O, do not change their valence states, you can give an estimate that the vanadium ions will be oxidized from 50% of vanadium 2+, 50% vanadium 3+, to 50% 3+, and 50% 4+. But the tricky problem is that how do we know which of these vanadium ions are 3+ and which vanadium ions are 4+? How do we know where the charge transfers to? And we use CHGNet to calculate the maximums on the unrelaxed structure and the relaxed structure, so the blue one and the orange one. And on the left plot, we show the vanadium ion maximums are well separated into two peaks after the relaxation. The two orange peaks correspond to vanadium 3 and vanadium 4, which were formed with the ionic arrangements that breaks the symmetry. To prove to you that we're not just trying to predict this valence states information from these really high-dimensional vectors are randomly distributed in a super high-dimensional space, on the right, I also show you the two-dimensional principal component analysis on the vanadium ion feature vectors for both before and after the relaxation. And you can clearly observe the latent space clustering of different valence states in the two orange distributions. And this result shows that the vanadium ion feature vectors are actually highly correlated with their maximums. So since this is a principal component analysis, you can see actually this valence charge degree of freedom is their principal degree of freedom. And in figure A, we also plot the DFT referenced maximums in these red dashed lines. And as you can see, forcing these orange two orange peaks to converge towards the DFT values, we're essentially applying a regularization in the latent space on the right that force these two orange peaks to separate from each other. And in this way, it serves as a charge constraint to encourage different behavior of vanadium-3 and vanadium-4 as represented in the CHGNet. And the next example is about lithium manganese oxide cathode material. Lithium manganese oxide cathode material is known to phase transform from the orthorhombic phase, shown on the top left, to the spinel phase, shown on the top on the bottom right. And this happens spontaneously through electrochemical cycling, which leads to irreversible capacity loss that essentially prevents its usage as a commercial high capacity cathode material. And the in situ XRD studies done in the early 90s shows a clear transition from the initial orthorhombic characteristic peaks in the 2 theta equals to 15 degrees to the final spinel characteristic peaks in the 2 theta equals to 18th degree that resembles this phase transformation from the orthorhombic symmetry to the spinel symmetry. To investigate the mechanism behind this phase transformation, we applied the pretrained CHGNet to run NVT molecular dynamic simulations on a partially deleted lithium 0.5 manganese oxide cell at elevated temperatures for 1.5 nanosecond. And the simulated XRD pattern from the snapshots in the MD shows a clear transition from the orthorhombic phase to the spinel phase, with the decrease in the 15th peak and the increase in the 18th peak. And the initial structure and the final structures are plotted on the right, so they can show the migration of both lithium ions and manganese ions that accommodates this phase transformation. But the story of this lithium manganese oxide phase transformation is actually far more complicated and far more interested than just the structural transformation. To convince you, let's look at how this mechanism was proposed in the early 2000. So John Reed, actually an alumni of Cedar Group, proposed this two-stage lithium manganese oxide orthorhombic to spinel phase transformation. In his proposal, this phase transformation happens in two stages, which in the first stage is a highly mobile tetrahedral manganese 2+ ions formed by this octahedral manganese 3+ ions charge disproportionation. And the second stage happens with the slower process of this tetrahedral manganese 2+ coordination rearrangement with the octahedral lithium ions. And if you write this in a simple chemical reaction formula, it looks like two octahedral manganese 3+ ions transforms into one tetrahedral manganese 2+ and one octahedral manganese 4+. And the hypothesis is made in this way, since in a quasi-static NEB calculation, the manganese 2+ ions are shown to have a low migration barrier as compared to the manganese 3 and manganese 4+. So that's why John Reed made this proposal that it's only through the formation of manganese 2+, these manganese ions are able to migrate at a surprisingly high speed at room temperature electrochemical cycling. However, in year 2003, Yemin Chang's group from MIT performed a magnetic characterization experiment on this partially transformed lithium manganese oxide. So here's what they did. They start with the lithium manganese oxide orthorhombic cell, and they deleted it by charging to 4.8 angstrom, which essentially removes more than half of the lithium to form a lithium 0.39 manganese oxide partial spinel structure. And these are the XRD characterization they have performed with these structures, where you can see again the decrease of the 15th peak and the increase of the 18th peak. So by performing a zero field cooled and field cooled magnetization characterization experiment on both the orthorhombic starting material and this partial spinel material, they obtained this magnetic susceptibility versus temperature plot. And by fitting to the Curie-Weiss law, what they found is surprisingly, low spin and high valence manganese ions on the tetrahedral sites. So on the other, in other words, what they estimate is that they show there are actually more tetrahedral manganese 3+ and 4+ ions than what has been proposed by John Reed, only manganese 2+ ions on the tetrahedral sites. So obviously there's a contradiction here, where John Reed argued that this lithium manganese oxide phase transformation is facilitated by this tetrahedral manganese 2+ formation due to their low migration barrier. Yang Zhang found in their characterization experiment that this tetrahedral manganese ions in partially transformed lithium manganese oxide cell show low spin and high valence states through their experiment. So the question for us to answer is, do these tetrahedral manganese ions really have low valence states in this lithium manganese oxide cell? And what is actually the mechanism of this phase transformation and charge transfer that makes this degradation of lithium manganese oxide cathode material happening so fast at room temperature? So to answer this question, here's what we highlighted by the power of our CHGNet. So here in the upper plot shows the distribution, shows the potential energy of lithium manganese oxide cell in the black curve together with the orthorhombic peak intensity and the spinel peak intensity. And the lower plot shows the distribution of the magnetic moments on all the manganese ions as a function of time. So you can see at the early part of the simulation, the mag moments of the manganese ions are mostly distributed between 3 μb and 4 μb, which correspond to manganese 4+ and manganese 3+. At around approximately 0.8 nanosecond, there is a significant increase in the amount of manganese 2+. So you start to see the emergence of this top peak, which is actually accompanied by the dramatic decrease in the potential energy and the increase in the spinel feature. And following this major phase transformation point, the manganese 3+ ions undergo a charge disproportionation reaction, resulting in the coexistence of manganese 2, 3, and 4 in a transformed spinel-like structure. And this result indicates the lithium manganese phase transformation is highly correlated with charge transfer. And the formation of manganese 2+ ions in the charge disproportionation reaction only happens in the long time scale of around 1 nanosecond, which is really impossible to simulate using any previous methods. And to validate our observation with CHGNet, we calculated we sent the structures in the 0.4 nanosecond and 1.5 nanosecond CHGNet MD to spin polarized DFT calculations. And the DFT results shows actually a highly consistent distribution of this tetrahedral manganese 2 and 3 ions as compared to CHGNet long time MD. So DFT also rediscovers that in the early part of the simulation, we have both manganese 2 and 3 on the tetrahedral sides, while in the latter part of the simulations, most of these tetrahedral manganese ions becomes manganese 2+. So this observation actually leads to a new theory that we have discovered for this charge transfer and phase transformation in lithium manganese oxide material. Here, we separate in the plot showing this slide, we separate the octahedral manganese ions from the tetrahedral manganese ion by counting the number of oxygen bonds to the manganese. And what you can see that is over 1 nanosecond time period, the octahedral manganese ions have a gradual decrease in their valence states, while the tetrahedral manganese ions have a increase in their valence states. Oh, sorry, have a decrease in their valence states. And this result actually tells us that this manganese 2+ formation is correlated with a long-range spinel ordering formation, which we see in the MD is around the timescale of nanosecond, rather than the previously proposed short-range tetrahedral occupations, which is around the timescale of picosecond. And and we rationalize this observation by arguing that this Young-Taylor active manganese 3 ions, which is dominating in the species in the initial cell are actually highly favored when the highly distorted orthorhombic phase is still dominant. And the manganese 3+ will only start to charge disproportionate to this manganese 4+ and manganese 2+ after the lattice strain is released with the spinel ordering formation, which is at the time scale of nanosecond. So in the third example, we apply CHGNet to solve the configurational entropy in lithium iron phosphate. The configurational entropy in lithium iron phosphate comes from both ionic entropy and electronic entropy. And specifically, the ionic entropy arises from the lithium vacancy interchange, and the electronic entropy arises from the interchange of the iron 2+ and iron 3+, and essentially the distribution of the electrons and holes. And figure A on the left here shows a temperature-dependent experimental phase diagram of lithium iron phosphate, where the x-axis is the fraction of lithium and the y-axis is the temperature in Kelvin. And you can see at low temperature, the lithium removal through the miscibility gap between a high lithium and low lithium phase. And around 400 K, there is an unusual eutectoid transition into the solid solution phase around x equal to 0.5. And early theoretic study shows that electronic entropy is the main driving force for this finite temperature transition from the two-phase region into the solid solution. And figure B and C are both simulations from DFT with cluster expansion methods, which allows Monte Carlo sampling. And with the difference that figure B considers both ionic and electronic entropy from lithium vacancy and electron hole, while figure C only considers the distribution of lithium vacancy. And the correct physics that's involved in this eutectoid transition is only captured in a model where both ionic and electronic degrees of freedoms are considered, where this figure C shows only a simple miscibility gap that does not match to the experimental phase diagram. So we use the fine-tuned CHGNet for both energy and electronic state calculation in combination with the cluster expansion to run the Monte Carlo simulation to simulate this temperature-dependent phase diagram. The result is shown on the figure C and D on the right. So we qualitatively recover the correct behavior of electronic entropy induced eutectoid transition, so which shows that the CHGNet captures the correct distribution of electrons and holes. And for comparison, any machine learning potentials without charge information, even the ones that would probably achieve 0.0 energy and force errors, will result in this wrong phase diagram as shown in the figure D. And such result highlights the importance of explicit inclusion of electronic degrees of freedom in materials modeling and construction of machine learning interatomic potentials. And the last example I want to show today is activated lithium diffusion network in lithium nanometeorite. So in this example, we show that the pretrained CHGNet without any additional data in this chemistry can capture the drastic nonlinear dynamic response that happens within the system. So previous AIMD studies shows the garnet lithium ion conductors have a drastic nonlinear response to compositional change. With stuffing one extra lithium into lithium 3+ delta structure, we have orders of magnitude increase in lithium ion diffusivity. So the pristine structure have a composition of lithium 3 LTO, while we put a small amount of lithium excess into this framework to have a lithium 3+ delta LATO materials, and we simulate the diffusivity of the lithium ions in this molecular dynamic simulation. And what we found is that the CHGNet correctly recovers this diffusivity, first of all, at the pristine structure, where the green curve is the AIMD result and the yellow curve is the CHGNet result. And we matches the diffusivity with the unstuffed structure and significantly decrease the error bar here that's given by AIMD. And moreover, we also were able to simulate this blue curve, where we have a very high activation energy of more than 1 electron volts, and which actually surprisingly matches very well with experiment values. But these types of dynamic process simulations with extremely high diffuse activation energies were not able to simulate with the AMDs, because these ion hops are rare events to be sampled. Essentially, the AMD cannot reach the timescale that are required for these types of simulation. So in summary, today we argued the explicit inclusion of charge information is an important goal for this next generation machine learning interatomic potentials. And in this work, we demonstrated the early success in CHGNet as a pre-trained universal machine learning interatomic potential that achieves charge regularization and inference from an explicit inclusion of magnetic moments. And we also show that the CHGNet pre-trained on this massive more than 1 million structures MP trajectory dataset offers new insights into electron-coupled physics in ionic systems. With that, I would like to take any questions. And thanks.
Well, thank you.
Yeah.
Thank you very much, Bowen. And on the interest time, I think maybe we should proceed with questions. There's already a number of questions here. Excellent talk. I was told actually the hot limit is actually 1.5 hours, not 2 hours. So I think we need to be a little bit more efficient now for this type of questioning. So the first question is from Hyung-Seo Park. He was asking about comparison between CHGNet with, let's suppose if you use other models such as CHGNet or M2GNet, would they produce the same basically accuracy? I'm not sure if MG2GNet even include Magmon as part of the descriptors, but I will let you answer that question.
That's a great question. So first of all, in a statistical limit, we have found that CHGNet definitely achieves the state-of-the-art performance in this new materials discovery task. And if you're looking for specific cases where we found that CHGNet performs better than the previous models, where they did not include the charge distribution in the formulation of their models. Let me see if I have that in backup slides. I might have it. Oh, yes. So this is a slide that we have tested. This is a lithium manganese oxide cell that we have relaxed with both CHGNet, M3GNet, and DFT. So on the left is the initial structures, which we removed half of the lithium ions from this lithium manganese oxide cell. And we relaxed this with M3GNet, CHGNet, and DFT, and these are the convergent structures. And obviously, by a glance, you can see the CHGNet one is more closer to the DFT one. But more importantly, if you send these structures to perform an electronic state calculation, what you'll get from the M3GNet structure is that the magmums within all of these manganese ions, which are in purple, I believe, is only a giant peak, is one Gaussian peak. But this CHGNet relaxed structures, the magmums on all of these manganese ions separate into 2 peaks that resembles manganese 3 and manganese 4. This is one of the examples that we have found.
So in essence, the reinforcement of essentially point charge analysis that is included in your new code allows you to be able to essentially discern in terms of the positions of these atoms then.
Yeah. So basically, because during training that we always force the manganese ions to have either 3+ or 4+ ions. So during prediction of these forces and energies, CHGNet drives them in either the 3+ way or the 4+ way, which results in these structures of containing both 3+ and 4+ ions.
All right, so more questions. So let me proceed. The R2 score looks slightly low, close to 0.7, as shown in the paper. Do you think which data of CHGNet struggles to predict?
So the R2 square here, I would say it's actually not low. This is a very high R2 square. R squared. So first of all, this number here are not just the errors that we predict on the structures. These numbers, we get these errors by taking the same initial structures and relax them, and we compare their final energies with the DFT relax energies. So there are two factors of errors, one coming from the different relaxation and one coming from the static calculation of the final frame. So if you combine both aspects, this 0.7 R squared, I think it's well, at the scale of the data set that we have currently, it's actually the highest R squared that we can achieve. And on the left, maybe this DAF that we show you is basically the discovery rate acceleration that using CHGNet as compared to using a dummy model in trying to predict the stable materials. So we have more than 3 times more efficiency in trying to identify the stable ones from the unstable ones.
Bowen, in fairness, if you look at paper, this is from Ong's group with the M2G-net, they also listed, of course, it's a fundamental potential, right? So that's also comes with the territory, perhaps, of a challenging of predicting the energy, for example. But in their paper, for example, they also try specific regions where essentially, presumably, this will be a fine tuning. And they were able to reduce, for example, their energy in terms of their RMSE to single digits for specific type of elements, for example. Do you think if and I guess this is still within the same line of accuracy, do you think if in the CHGNet, if you were to do something more of a fine tuning like that, would you be able to reduce your energy? Because I see that the version 2 and version 3, your energy levels, of course, it's still below the chemical accuracy, people usually call it that, right? Which is 1 kilocalorie per mole, which is something rather 40 something, and you guys have beat that already to the 29. But can you get to the single digits? Can you get to like if you look at, for example, DPLR, for example, they can get it to like 2 millielectron volts.
Yeah.
So what do you think about that? Yes.
Yeah. So it's very, first of all, it's very different from pre-training and fine-tuning. When speaking about fine-tuning, single digit is actually very, very easy. So from our experience with fine-tuning challenge, like we often get 1 MeV per atom or 2 MeV per atom. And so I would say it's a very different criteria to compare against this and the fine-tuning accuracy. And yes, when we do have the data in the chemical system that we want, we can typically reach several MeV, typically around 1 and 2, and around 40, 50 MeV per angstrom force error.
All right, excellent. I'm gonna skip the second one because presumably you're gonna demonstrate this with perhaps you're gonna be running maybe a Jupyter or something like that.
Yeah.
So let me just skip to the third questions. In these 3 specific application, in a particular case of lithium manganese dioxide that require MD simulation, was the model fine-tuned with additional data to be simulated, or everything is out of the box application of the general model?
No, everything that's shown today in the applications are only trained with data within MP trajectory dataset. So there's no extra data that's in any of these systems.
All right, yeah. The next question, suppose I want to include van der Waals interaction to the model. I think since you said you get all the data from MP, I don't necessarily that becomes like a standard correction. Can you do fine tuning on top of CHGNet?
Yes, that's a very good question, and the answer is yes. So CHGNet is trained on all the GGA and GG plus U calculations from Materials project.
Okay, but and I guess in the meantime, while we wait for Professor Sakidja to return, there's a question that's asking, can you please repeat your answer regarding including the van der Waals correction, and if CHGNet can be used for layered van der Waals structures, or at least for substrate plus absorbate systems?
Okay, So to answer this question, so first of all, CHGNet is trained on all the GGA and GGA plus U calculations from materials project, which essentially in the DFT frameworks, our training labels do not have the van der Waals corrections. But on the other hand, it depends on how important this van der Waals correction it is in your system, and whether you can reproduce some meaningful results with only GGA and GGA plus U. And you're welcome to give a try in this system, since the formalism and all the codes and ways of our models are open sourced. It can be very easily to try this out. And if the missing of van der Waals correction in our training data does have a very large impact on your system in interest, we also encourage you to try to fine tune of our model using data that does have this van der Waals correction. We have tried that, so we have some studies where we also involve van der Waals correction, and we have tuned CHGNet with the corresponding DFT labels that have turned down van der Waals corrections, and we reproduced better results than the ones that do not have the correction.
I think we should be back.
All
If your question wasn't answered, do you mind retyping it in the chat, because we might have lost some of the questions.
Okay.
Right. Back over to you, Professor Sakidja.
Yeah, I'm sorry, I don't know what's going on, but
Yes, that was a mistake on my end. Sorry, that was
right.
someone started another link somewhere and then it ended this one.
Yeah. So I think in the interest of time, I think well, okay. So I see there's a new question. Let's take care of these two questions, and then we'll proceed with a demonstration for the code. What is the computational cost of training? And then maybe if you can lump sum that with the second question, which is, can you comment on the comparison accuracy of the two potentials, CHGNet and MG2GNet, in modeling ionic systems without variable charge elements?
So the first question, the computation cost of training CHGNet, this is typically at the scale of hours. So if you have a data set of several hundreds of tens of Ks of MD structures, or even hundreds of K of structures, and you typically fine-tune CHGNet for tens of epochs, and this is a matter of hours and at the most 1 or 2 days on a single GPU. To give you a scale of the time that we use to pre-train our model on this giant MP trajectory data set, so it's 1.5 million structures, and we used around 8 days on a single GPU. So it is a manageable time. And the second question, the comparison of accuracy of CHGNet versus MTGNet on systems without variable charge elements. For this question, I believe the answer, CHGNet still has a slight higher accuracy than MTGNet. And this can be observed from the accuracy in the relaxations in the MathBench discovery task, where essentially during the relaxations, there is no valence state change. And CHGNet still performs better than the task compared to previous machine learning potentials.
All right, thank you very much. I do actually just have very quick questions. When you make this projection, it's a linear projection, right?
True.
By which, is there a way to further improve it? I know it's already low anyway in terms of the error with respect to your magnetic moment. But if you were to think about ways to do this, can you insert, for example, DNN into the system rather than the linear projection that you have right now? And the second one I want to ask you is basically, as far as the, I know this is obviously a very big challenge in terms of reducing, as a fundamental potential, the energy, the RMSE for the energy. Can you think of like what are the ways to further reduce that energy error? Because I think that's something obviously people are aiming to do. Yeah. So with that, then maybe we can after that you can proceed with the training.
Yeah, really great questions. So the first question is, can we use if I understand it correctly, can we use a more sophisticated layer to predict the charge so that we have a lower charge accuracy? We have a higher charge accuracy. The answer to that is, of course, yes, but we don't want to do that. And that's because we want to apply these linear layers as also a charge constraint to this atom embeddings, so that basically we are enforcing the learning of charge to goes into the deeper layers within the graph neural networks, but not these projection layers. So that, but if we restrict the prediction of charge to go into the formulation of the graph layers, then this part of the layers are shared between charge and energy. So since we think charge and energy are highly correlated, what we want these two tasks to share a lot of parameters instead of using most of the parameters from each of their own. So that's why we only use a very shallow layers to predict a charge. And the answer to the second question, so what are the possible future directions to further decrease these errors on energy forces? From my point of view, I think the most essential efforts might be a better data set for this. So as you can see, CHGNet almost utilize everything that we have at the moment for materials project. And all of these models trained on materials project, I would say have actually very similar errors. It's a matter of few MeVs. And if you want to decrease another 15, 20 MeV, my belief is that this can only be done by a better data set, a larger data set. That is, yeah.
Okay. I mean, for the interest of time, I want to round these two questions. Essentially, this is more of an improvement. Let's suppose if I use different functionals or I include some type of obviously corrections, such as Grimm's correction, for example, for VWD, VDW. The question I have is basically because you already use this pre-trained big database, right? Which obviously is carrying a big weight, obviously, in terms of your model. If I were to combine this, for example, let's say with the correction, let's say D3 or whatever the correction is, those are big correction in energy, as you know, right?
True.
Because
True.
you just look at that. So it's not a trivial way of just making this projection in terms of after you do correction. So do you think it's, I guess, two scenarios? One is completely just upgrade all of the database to include, for example, van der Waals correction, or you try to essentially add maybe a smaller data set, because usually it will take some time anyway to do VWD corrections, and then somehow being able to correlate that with your big data. Which way do you think it's sort of a more practical in the sense?
Yeah, so the energy shift coming from these VDW corrections are twofold. First of all, there is a systematic energy shift by adding these correction terms, and which I think is a larger shift as compared to the actual relative shift within these VDW corrections. So for the systematic shift, it's easier to solve. For example, we can find the average shift of the chemical system that you're interested, and you can just minus that number from your labels so that your labels becomes more consistent to charge and predictions. And that's a easy solution to the systematic shift of the energy. And on top of that, there's a relative shift energy, which is comes from these extra VDW interactions. And to solve these questions, I believe it's better to have more data set within your system of interest rather than generating a data set spanning the chemical periodic table and retrain CHGNet. Yeah.
Okay. Thank you. And again, I want to thank Bowen, and maybe we can proceed with demonstration in the interest of time. we only have about 15 minutes. And again, excellent talk. And then obviously, if you have any questions, more questions, feel free to contact Bowen and Professor Cedar's group with this, or download the GitHub first and then try it out yourself, obviously.
Okay. Can you see my notebook?
Yes, yes.
Okay, so the code examples that I'm going to show today are mainly coming from our Cedar Group CHGNet GitHub website. So you can retrieve these notebooks. They're very similar with slight modifications. So these are already on our GitHubs, and you are welcome to retrieve this after today's talk. So in the first notebooks, I'm going to show you some basic calculations that you can do with the pretrained CHGNet. So if you open these notebooks here, first of all, you have to install CHGNet, and this can be done through pip install CHGNet, which will CHGNet is actually a quite clean package. It has only a few dependencies that includes PyMatGen, which is the infrastructure from Materials project, and also ASE, atomic simulation environment, which is the essential dependency that we use to run the MDs. And of course, PyTorch that we use to implement these deep learning models. So first of all, if we can input CHGNet by this simple line from pip CHGNet.model import CHGNet. And here I show you how we load a structure using PyMatGen. This example here shows you how to load these CIF files that is saved on the disk into a PyMatGen structure, where essentially you have this structure that has all this crystal lattice information and also the site information. And to define on CHGNet is essentially just one line of code. CHGNet equals CHGNet.load. And this line here, by default, in the package version that we published this week, loads 0.3.0. So this line is the same as CHGNet.loads. If you want to access the previous version that we performed all the experiments in the Nature Machine Intelligence paper, you can do 0.2.0. But the 0.3.0 is considerably better than the previous one. And to use, if you have any device that can make your calculation faster, for example, I'm showing you this notebook on my MacBook with the Apple Silicon GPU acceleration. You can do CHGNet to MPS, and this essentially moves your CHGNet data onto your CUDA or MPS object. If you have CUDA, you can do CUDA, but here it will give me an error because I don't have CUDA. So this is a way that you move your model to your corresponding device for faster calculation. To predict the energy and all the properties is just one line of code. Prediction equals to CHGNet.predict structure, and you give the structure into this function. And here you can see it's within 1 second, it gives you the system energy in EV per atom, the forces on each atoms, the stress, and also the predicted maximums. And after we have these are the essential components for machine learning potentials. We can inject these informations into, for example, a structure optimizer, so that we can use this force information to relax a structure. Here we initialize a relaxer object, which is loaded from CHGNet.models. And here we set use device equals to MPS again, and the optimizer we use a BFGS, which is a second order optimizer, and we want to perturb this structure a little bit, right? So apply a 0.2, 0.2, 0.2 strength to it, and we perturb the atoms a little bit, and we see if the CHGNet can relax back the initial structure. And you can see the relaxation happens at the order of seconds. In a few seconds, the relaxation will be complete. And we actually applied a considerable amount of strain in the structure. And if you print the initial and final result, you'll see that the relaxed energy gets back to the pristine energy. And also the volume, we basically twice the volume, and it gets back to the initial volume. And in the next example, this is a more realistic and a harder case, is how you do oxidation state calculation from CHGNet. So here we again have the structure. The structure here, let me remind you, this is a lithium manganese oxide structure, which is actually the orthorhombic structure that I discussed in the talk. So it has 8 atoms. And let me make a supercell of this structure. So you can see the composition of this supercell. We have 16 lithium plus, 16 manganese 3 plus, and 32 O2 plus, and this is charge neutral. And we randomly removed half of the lithiums in these systems. So you can see after we remove half of the lithium, we get only 8 lithium ions. And now this is charge unbalanced. And we want to see which of these manganese ions will be oxidized. So we can just perform a relaxation with CHGNet. This will be a little bit longer since this cells has 8 times atoms of the previous example. But still, I think it can be completed around 1 minute. And here you can see, it essentially tells you the time that's taken at each step, at the total energy of the system, and also the maximum force that's experienced by these atoms. And the F max here is actually an effective force that combines both the forces on each atom and also the strain on the stress on the cell. Yeah, it's completed. And if we tries to read what are the magmums on both the unrelaxed and relaxed structure, here I plot you the magmums on between 3 and 4. You can see in the unrelaxed structure, it's only 1 peak. After relaxation, you separate it into 2 peaks. This peak corresponds to the manganese 4, and this peak corresponds to manganese 3. And how do we actually apply these magmums and transform into charges? You can use this function. You assign, for example, 2.5 to 3.5 magmum to 4 plus, and 3.5 to 4.2 to 3 plus. And for better visualization, I'm replacing the 4 plus atoms into a nickel 4 plus, so that I can save the structure. And let me show you what the structure looks like. Okay, if I open this structure in Vesta, you can see all these gray ones corresponding to nickel, these are the 4 plus, and the purple ones are 3 plus. So it's really hard to distinguish the purple ones and gray ones just from a look at the geometry. It's not possible that you can decide their valence states, but CHGNet can differentiate them. Half of them should be 3 plus, half of them should be 4 plus. Okay. And the next example is how to do molecular dynamics with CHGNet. So again, you load this molecular dynamics object from CHGNet, and CHGNet allows you to, first of all, input an atoms or structure, Pymagian structure or ASE atoms into this object. And here we use the relax structure from the last step. And you assign model to it, and you give an ensemble. Here we use MVT, a temperature, and also a starting temperature. And we run this simulation with 2 femtoseconds. And actually, you can change the thermodynamic. You can change the thermal bath here. Here, it defaults to Berkeley thermostat, and you can also use News-Hoover or other thermostats. And we save this to these files. And here we run a 50 steps MD, and the md.log file will pop up instantly in your file system, and you can see it's updating. So every line corresponds to one MD step. So it's happening really fast. And remember, this is running on this MacBook laptop. If it's on a GPU machine, it's much faster than this. So I only run this MD for 0.1 picoseconds, so it should end in a matter of seconds. Okay, that's it. That's a 0.1 picosecond simulation. And if I show you what happens in this MD, so here I save all the frames in the MD. First of all, the MD is saved in a format where we call MD out trajectory, and this is a ASE trajectory object. To read how you can manipulate with this trajectory object, you should really go into the documentation of ASE, and this is the trajectory documentation in ASE. For example, you can get every frames and the properties of every frame within this trajectory. And here, let's save all the frames in the MD to my laptop, and I'll show you the motion of these atoms. Okay. So in a matter of minute, we already can make these nice videos of the movement of all the lithium and manganese ions within this system. Okay, that's basically the basic usage of CHGNet as a force field. And the next, I'm going to talk about briefly how you can possibly fine-tune CHGNet to your own needs. So first of all,
I'm sorry, Bowen, I was told that we have gotten an extension till 11:45. So please indulge more on the pre-training or training.
This is very
fast.
Yeah. This is very fast. Okay. So again, we load the CHGNet, and first of all, you need to parse your DFT outputs into a readable format of CHGNet, and this is basically PyMagine structure. And this part, you can read the documentation in PyMagine, how you load your, for example, how you parse your result from VASP into PyMagine readable formats. What we basically need is a list of structures and a list of the labels. And here, what we have created is, since we don't have DFT in this demo, I just create a dummy data set of 100 structures, and the labels of all of these structures are basically, for example, just coming from the prediction of CHGNet. So I use CHGNet to predict the energy of each of these structures, and I add a small noise and use them as labels. So it's very simple. How do you define a data set? You pass all of these structures and your labels energy, forces, stress, and magmums into this data set that you import from CHGNet, and you create these data loaders that essentially define the ratio of your different set and also the batch size. And now you define a trainer. Optionally, you can freeze some of the layers to retain most of the knowledge from the pre-trained weights. And in the trainer, you define your optimizer, your learning rate, and your criterion and stuff here. Just by click, you start the training. Trainer.train. So the training will typically, it's also very fast. This demo will probably complete this training in a matter of minutes. And after this training, the models gets saved automatically to your disk, and you can also load these models by the trainer. And that's it. That's basically it. And we have some extra discussions here about the compatibility issue and also the elemental reference energy. That's basically what we have been discussed in the van der Waals correction issue. Yeah, that's all I want to show today.
All right, thank you very much. We have a little bit more extra time, so I think there's some additional question here. If that's okay with everybody, still stick around. I'm gonna read the question from Professor Jin Cheng Du. How easy is it to extend the training of current model with additional set of data for a particular system? I presume you already shown this.
Yeah.
And I think maybe within the context of, for example, improving the the accuracy, and where you start to add more of the, let's say, for the long range interaction and so on, so forth. A technical question: convergence of the magmon in a complex system usually will take some time. So how do you ensure the convergence of this data set?
All of the data that we have collected for the training of CHGNet are strictly converged. So we have go through all the convergence check in materials project, and we have enforced every step that has a spin polarized calculation, which provides maximums, needs to be converged.
Well, if you were, I'm sorry, if you were to add additional data of, let's say, higher accuracy, maybe use meta GGA or something even higher in these, ladders, sort of a Jacob's ladder of your functional. Are you worried that linear sort of regression projection is not good enough to be able to accommodate the difference between, let's say, your new addition with the pre-trained data?
Oh, you mean the maximum with the linear projection?
Yes, yeah.
Of course, the maximums is not only predicted by that linear layer. It's predicted by linear projection of the atom embeddings, and the atom embeddings are calculated through all of these graph convolution layers. So if you are, so this is for users to test out, right? There's no answer for sure to this question. If the accuracy is not enough to your maximum prediction, that's essentially saying your functional has a large deviation from the GGA functional that we used in materials project. For sure, you should enable more layers to be flexible during your training. And if you have a small deviation from your dataset to materials project dataset, then there's a small deviation, then you should only train a small number of layers. So this is for the user to test out.
Okay, one last thing, actually, I just want to have another question it comes in mind. Obviously, this is reliance on the magnetic moment. So if I were to deal with, essentially, because your example here essentially showing that very well, we're able to discern that. What if you have the system that is obviously, let's say, in the non-magnetic cases where obviously now your correlation may not be as good?
That's very true. One of the cases, of course, lithium, because lithium, the electrons in lithium in these metal systems are not localized, and we're not able to get the localized magnetic moments. In this case, we're not able to infer the charge states based on the mag moments. But luckily, we can still learn from the local environments of different, for example, coordination numbers to differentiate the different behaviors of different types of atoms. It's just that we cannot identify their charge states from their magmas, because this is not possible even with DFT.
In the let's say in deep MD, as you know, they actually evaluate the Wannier centers, right? And by which now DPLR, for example, and so you get the dipole and be able to insert that actually as part of your way of basically predicting your energy. Do you foresee something more complex analysis? As because it comes basically with vast calculation, basically, right? When I invoke Wannier 90, for example, I can get all those information as well. Would that be useful in terms of to add into your point charge analysis, for example?
I believe it will be useful in that case. The reason why we did not include all of this in properties in the formulation of charge is because the most obvious reason is because MP does not have those. Some of those informations have been lost, and we are fine-tuned. We are pre-trained models, so some of the designs are coming from the dataset itself.
Let's see, what else? Is there any other question that I miss?
So I can ask a question in the meantime.
Okay, go ahead, please. Yes, Keith.
So I would believe that magmom is very highly correlated to coordination. When you look at the coordination of, say, a manganese ion in I guess you're showing some solid electrolytes there. How much of that do you think is more a structural property? So could I, for example, do some sort of coordination number analysis and extract good maybe charge state predictions? Have you compared that to just doing some coordination number analysis to predict the charge state?
Yeah, that's a great problem. Yes, I have inferred for several times, like the different valence states of manganese ions usually have different coordination numbers, but sometimes the difference in this is so subtle that it's obviously not possible to perform using coordination analysis. And one of the examples is this example I just showed in the notebook. Here, all the gray ions are 4+, and the purple ones are 3+. I don't think it's possible to differentiate them just using coordination number. They look the same with exactly same coordination. They might have minor difference in their Young-Taylor distortion. That's how we differentiate 3+ from 4+. But again, it's very hard if you use very simple or classical ways to classify the valence states.
I'd like to chime in on that actually, because I think it reminds me because I know Jin Cheng is asking the question, and for example, if I evaluate something more of a, let's say a molten salt, right, which is essentially it's a liquid state, and a lot of times actually the analysis you really want to get is if I introduce some type of impurity in the system, let's say if I have multiple valence states. Into otherwise would be say FLINAC or FLIPE or those type of molten salts. Usually you will end up getting this distribution if you run this with ab-initio MD of charges. Would CHGNet be able to essentially be able to replicate that? And I think that would be a good way to test whether or not this sort of point analysis is able to not just like a binary choice, but more of a multi sort of valence state in a more sort of a challenging environment.
Yeah, I see your point. So I think the answer is yes. If you still remember the plot I showed for the charge distribution of the manganese ions in the lithium manganese oxide case, it's not a sharp peak distribution of the manganese ions because the system is at more than 1000 K. Everything is at elevated temperature, high energy points on potential energy surface. They're not just ground states, even electronically. So you see all these maybe intermediates between 2+ and 3+, but statistically you still see the distribution that's centered at 3 and 4.
All right. Okay. Any other questions? We still have a few more minutes. Where do you see if you have a let's call it version 4 now, I suppose, because you have a 3 just came out. Where do you see is like sort of the next target to drive home more improvement in CHGNet in your view?
That's a hard answer for me. We don't have a clear plan for version 4. Might be if there are better data sets coming out, we can train CHGNet on those. That can be a possible version 4. And other than that, there might be we might think of corrections on the model itself. For example, adding some electrostatic repulsions, and we do see such types of problems, but where if nucleus gets too close to each other, and CHGNet is not predicting the energy correctly, and that's essentially because there are no such data points in materials project where you have overlapping nucleus, and such data points are even not DFT sampleable. So how to characterize these parts of the potential energy surface correct might be interesting for us to avoid some extreme cases. But normally in MD, those are not we never experience these issues.
All right. So well,
I think there's a couple more questions in the Q&A. If we can just wrap up those and then.
Right. Yeah. Let's do that. Actually, one question, and again, you can contact Bowen. You can contact Professor Cedars group as well if you have more questions about this. Let me just say. Let me just post the last question, and I'm sorry if I can't do the rest. If I understand correctly, CHGNet is invariant rather than equivariant GNN. Would you comment on that?
Yes, CHGNet is invariant, but the forces are calculated by auto differentiation of the energy. So the forces are strictly equivariant. So if I rotate a structure by a certain degrees, the forces are deterministic to be rotated by the same degrees of angle. So even if the energy itself is invariant, the forces are strictly equivariant.
I think the question is more along the lines of, so it seems you use only invariant features in your network as opposed to something like NeQuip or MACE, which uses higher order equivariant features. I think that's the difference. That's what the difference that the question was looking for. So I guess NeQuip versus CHGNet.
This is a very hard question to answer. As you know, this is still an open discussion in the research field. Equivariance versus invariance. I think we've seen a lot of success coming from these equivariant models. And from my personal belief, I think equivariance is a method that you essentially restrict your functional form to realistically, people only use the first few orders of expansion in their equivariant models up to L equals to 3, for example. So that's basically limiting the form of your functional into a more physical form so that your model is more data efficient. That's my understanding for equivariant models. But if your model has a giant data set that spans the whole periodic table, that you don't care about data efficiency that much, there's really not that a big difference from equivariance and invariance. And that's what we have observed from the new materials discovery task in MathBench discovery, where the MACE structure, which the MACE model is equivariant, trained on the same data set as CHGNet and pretrained data set, but performs actually a little bit worse than CHGNet, even if it is equivariant. So I do think equivariant is good to some aspect, especially it is data efficient. But maybe for universal machine learning potentials, the benefit from equivariance is not that obvious.
Well, I suppose there is a saying, there is no free lunch. So you know, you balance between, you're aiming for fundamental potential, obviously, in this case. And I think that makes makes more sense in that sense because of the efficiency as well, and be able to cover a large range of input in. So I suppose we are only 4 minutes left. I think before I hand it back to Keith, I just want to say thank you for everybody. This has been a very nice presentation. A lot of questions, very insightful questions by the participants. So I want to thank all of the people there. And I think if I would to summarize this, this is obviously a new era in terms of being able to up the ante, I would say, about how AI can be used to evaluate systems that are normally it's very difficult to assess, right? So I mean, or it would be something where neural network can handle, but not in the more of a fundamental potential like this. So I think this is it's a great opportunity to delve into, especially with people that working with especially ionic system, I would say, where things are much more probably in this case immediately applicable. I think it's there's room for improvement, just like any program, I think, and I think some of this already been pointed out during our discussions, and I think it's I certainly look forward for your version 4, Bowen, and then see how those numbers can be even further down. And I, of course, like you said, it all depends also with the materials database that you use. And I'm sure you are working with, I know people in Materials Project obviously is working in conjunction and being able to produce more and more higher quality data, much higher than what we have now. And I think that will go in tandem with obviously the accuracy and so on and so forth. With that, I thank everybody. I'm gonna return back to Keith.
Yeah, thank you so much for that great perspective. Thank you. This was a great session with lots of interesting discussion. I wish we could go longer, but unfortunately we have certain time constraints. This video will be available, I think, next week, as well as all the videos from the previous seminars are now available on the MICDE YouTube website. So feel free to look back at those and share them. Next week, we're going to be taking a break, and then we'll be back on November 9th with a talk by Lens Fiedler titled Predicting Electronic Structures at Any Length Scale Using Machine Learning. So thank you all for attending. Thank you for your time. and see you in 2 weeks.
Thank
Thank you.
you.
Bye.
Bye.
Bye.